Okay, so today what we're going to do is we're going to continue our discussion of trying to define vectors on a manifold. And after that, once we define vectors, we'll be able to generalize to more complicated objects like tensors, okay, on a manifold. And so the way we started by trying to define vectors on a manifold is to talk about, so there is no, so, okay, sorry, let me just backtrack a second. So first of all, on a general space, okay, there's no curved space. There's no way to necessarily think about what a straight line means, right? So you can't draw straight lines on this curved space, on this arbitrary manifold. In fact, the notion of straight itself is not defined on a manifold because a manifold has no measure of distance. Okay, so in Euclidean space, we think of the shortest path between 2 points as the straight line. Okay, and the shortest path means that you have a notion of distance which you use to measure the distance between 2 points. On a general manifold, which is just a topological space which is smooth, okay, on which you can put these smooth charts, there is no notion of distance. Okay, so this is not the right way to define a vector, but intuitively we expect that, for example, suppose you have some kind of coordinates, let's say on your sphere. Okay, so imagine some kind of theta and phi coordinates. Okay, and some kind of grid like this. You might intuitively expect that at each point, right, I can kind of think of vectors which are kind of going along latitudes and longitudes. More intuitively, I mean, if I move away slightly from this intuitive picture, then I can think of this idea of what are called tangent planes, okay, which is at each point I can define tangents to the sphere. For example, if I have a sphere or any kind of two-dimensional surface, it's easy to imagine what these 2D tangents are, okay. But this visualization relies on embedding, okay. It relies on the fact that you're thinking of an S2 as embedded inside 3 dimensions. But you might want to not think about embedding, right? Because not every topological space necessarily can be embedded inside a higher dimensional space, or at least a higher dimensional space that you're imagining. So if I'm trying to embed an n dimensional space, it's not necessarily that I can embed it in Rn plus 1. Okay, this is not necessarily going to be true. Okay, for example, there are 2-dimensional spaces that cannot be embedded, okay, smoothly embedded inside R cube. Okay, so those are slightly more exotic examples, but we won't do them right now. Okay, so there's something called a Klein bottle, and so on. These cannot be. These are 2D surfaces that cannot be embedded inside 3 dimensions. Okay, and there's something called the rail projective plane. This also cannot be embedded in R3, but they can be embedded in R4. Okay, so the embeddings are not obvious, and so we'd like to talk about a notion of tangents which doesn't rely on the fact that this is embedded inside some higher dimensional space. Okay, and ultimately, of course, when you talk about space-time as 3 spatial dimensions and 1 time dimension, you don't necessarily want to start thinking about that as embedded in something higher, a higher dimensional space-time. Okay, so so if you only have your manifold, how do you define tangents on a manifold? Okay. And the way we said that, you can take this intuitive idea of a tangent plane, and you can think about, instead of thinking about tangents which sort of live in some space which is not on the manifold, you can think about curves, okay, passing through a point. So on an arbitrary manifold, you can consider a curve passing through some point P, okay, and we will use all these curves, a variety of curves, to define tangents. Okay, so we'll define the tangent to the curve at the point P. Okay, because again, the notion of calculus on the manifold is defined. Okay, we can define these tangents, and once we can define these tangents, we can start defining vectors as the tangent of the curve at this point. Okay, as we'll see, that's not far from the actual definition. Okay, so roughly speaking, the set of all tangents on all curves passing through this point P, roughly speaking, that will make up a vector space. Okay, so roughly speaking, the tangents will have all kinds of magnitudes depending on how fast the well, okay, I have to define these notions precisely. So let me just go back to the definition that we were trying to do. Okay, so what we did was we first had a map, we had a curve, okay, on a manifold, and this curve on the manifold, Okay, remember that we thought of it. You can always think of a curve on a manifold as a map from an open interval AB, okay, to the manifold. Okay, and you can of course look at this in a coordinate representation on a coordinate patch, okay, or in some region around this where a particular coordinate patch is valid. Okay, but the mapping itself, this mapping C, doesn't rely on the fact that you have a coordinate patch. Similarly, you can also define from the manifold as a whole, okay, you can define a map which we denote as F. Okay, so C is the map which defines the curve. F is a map which defines from any point on the manifold, it gives you a real number. So it's a function on the manifold. Okay, and we're assuming it's a smooth function. Okay, and we're assuming that this is a smooth curve, in the sense that when we think about these functions on coordinates, okay, these are differentiable. Okay, these are differentiable functions, infinitely differentiable functions. Okay, okay. So now this, since you have a map from this open interval AB to the manifold, which gives you the curve, and from the manifold to the real line, you can use this to figure out the composite map directly from the curve or this open interval AB to real numbers. So that is, for every point on this curve, okay, you're figuring out what is the image under F. Okay, so F basically can be evaluated along the curve. So in other words, you're evaluating F circle C. Okay, so you're evaluating F at every point along the curve. In a coordinate representation, you would think of this as F of x mu of t. Okay, so t is this parameter, okay, which lies between AB. X mu are the coordinates of the point, okay, on the curve. So for a given t, there's one point on the curve. Okay, sorry, there's one point on the curve, let's say here, and then I find the coordinates of that. The coordinates of that are x mu, where mu goes from 1 through n. Okay, so x mu of t gives me the coordinates of that point, and f of x mu of t gives me the value of the function. Okay, at that point on the curve. Okay, so we have two things. We have a curve C and a function f on the manifold. Okay, and now what we intuitively want to do is we want to define the tangent vector at C0. Okay, so why C0? We just took this arbitrary point t is equal to 0. And we said that that maps to our point of interest, okay, P. Okay, this 0 is nothing special about 0, it's just a choice. Okay, so the point where t is equal to 0 maps to some point P, which is our reference point on this curve. Now, what we want to do is at that point P, okay, which is C0, we want to define directional derivatives of this function f of Ct. Okay, so that is, we want to define the derivative of f of Ct, that is this f circle C, which is a map from the open interval AB to real numbers. But it's a derivative along the curve. Okay, it's a derivative along the curve. So this is a map from real numbers to real numbers. And we can, if we differentiate it, we'll get a value. That value is the tangent. And it's in the direction of the curve itself, okay, at the point P. Okay, so what we want to do is we want to define df dt. Okay, that is this quantity df dt, where this f is evaluated on the curve, and where on the curve this is evaluated at the point where t is equal to 0, which is our point of interest. Okay, where c of t equals 0 is the point P. Okay, so we want to define this derivative at this point, and this will give us a notion of a vector. Okay, now the point is that this derivative, okay, this derivative exists independently of the coordinate representation. Okay, so no matter what coordinates you choose on this coordinate patch to describe this point P, this derivative is a derivative of a function which is this f circle C. Okay, f circle C, which is the map from the open interval AB to real numbers. Okay, which is a function from real numbers to real numbers, so you can differentiate it. Okay, so this df dt is a well-defined derivative of that function, and the derivative exists independently of any coordinate representation, which means the notion of the vector that you're trying to define, okay, by this tangent, okay, or by the slope, is independent of any coordinate choice. Okay, and so that's what's nice about this kind of way of defining it, is that the definition doesn't really rely on the fact that you've got a particular type of coordinates on the manifold. Okay, so it's really a derivative which is associated with a curve. Okay, derivative associated with the curve C of t. Okay. Now, what you can do is you can use a coordinate system. You can use a coordinate patch to evaluate this derivative. Okay. The derivative exists independently of which coordinate patch you choose to evaluate it in. You will always get the same answer no matter what coordinates you use, but it's convenient to choose a particular coordinate system to evaluate the derivative. Okay. So, so let's see how to do that. Okay, so let me just make this a little cleaner, create some space. Okay, so this is our manifold. This is the interval AB. This is the point 0, and this is real numbers. Okay, C takes us from here to a curve. F takes us from this manifold to R, and in particular, F circle C takes us from the curve to real numbers. And now for this, some point P, we can find the coordinates. Okay, if we can find the coordinates, which will denote as x mu, which belong to the space Rn. Okay, and this is a map phi. Okay, and if I want to figure out what is this map, okay, that is from the open interval AB to x mu. Okay, can you tell me how I should denote that this map from the open interval AB to x mu? What is the right notation to denote that map?
Phi composition C.
So phi takes me from P to x mu. Okay. Yes. So so first I want to go here, then I want to go here. So it's first C, then followed by phi. So good. So phi compose C. In coordinate notation, there's a simple way to write it. This is a function, okay, from R to Rn, and so therefore this is just x mu of t. Okay, the set of all x mu of t. Okay, is this function phi? So specifying phi circle C is like specifying these functions. X mu is a function of t. Okay, now similarly, if I want the coordinate representation of this function f, what I want is this map. Okay, from the points to R, so from the coordinates to R. So how would I denote this? First using f and phi.
Phi inverse compose f.
Good. Phi inverse compose. No, not really. Now you have to be careful because you're starting from here. Okay, so what is the first operation you have to perform?
Okay, first perform phi inverse and then
first perform phi inverse. That'll take you back to the point P, and then
f.
Then f. Okay, and then that will move you onto real numbers. Okay, so this is the operation, and if I want to denote it using some kind of coordinates like this, how would I write it? F of
X mu.
X mu. Okay, so if you give me the coordinates of some point, okay, I'm evaluating f on that x mu, and this is a map from Rn to some open subset in R. Okay, so now what we're doing is, instead of saying let's look at f circle C, okay, f circle C, which is this function, which exists independently of any coordinate choice, what we're doing is saying, well, whatever this f circle C is, I can instead locate it in coordinates. So I can look at it as if first let me find the curve in coordinates. That is, let me find x mu of t. Okay, this will give me the coordinates of the curve at different points t along the curve. Okay, so t is a parameter. So t is equal to 0 is I'm here. Let's say t is equal to 1, I'm somewhere here. T is equal to 2, I'm somewhere here. I want to find coordinates, okay, in Rn that correspond to these points. Okay, I might have to use different coordinate patches. Let's not worry about it. Okay, so so we first do this. Then we find some set of points which are the coordinates of the points on this curve. For all these points, we now want to find what the function evaluates to. Okay, so that is, we're finding f not at all x mu's, but at x mu evaluated on the curve. Okay, so as we vary t, okay, we move along this curve, which is moving along this curve. So we're moving along these coordinates of the curve. Here we're actually moving along the curve on the manifold. Okay, and so therefore this function is essentially just evaluating f circle C. Okay, So this f circle C is evaluated in a coordinate representation like this. Okay, f of x mu of t. Okay, so as long as we're sticking with one patch, okay, where the coordinates x mu are valid in that patch, okay, so that is as long as I'm not exiting the patch, okay, so if I cross this patch, then I have to switch to a different coordinate system, okay. As long as my coordinates are valid, I can continue to use this kind of notation, okay. So in this patch, we can write the derivative, okay, that is we can write this f of ct, okay, we can write it as this is just an equation expressing what I just told you. Okay, this f circle C is f of ct. Instead of writing it as f of ct, we now write it as f circle phi inverse, okay, which is this operation here, okay, and compose with phi circle C, okay, which is this operation over here, okay. And the important point is that for this phi and phi inverse to be defined, you need to be in a valid coordinate patch, okay, which describes that the points on the curve. Okay, so now basically this entire thing can be written as f of x of t. Okay, that's what we were saying. So this phi circle C is basically giving me this x of t. F circle phi inverse gives me f of these points, f of x of t. Okay. Okay, and now what we have is, now that we have this function, okay, this function is, remember that this function is represented this way in a coordinate patch using f of x of t, but the function itself from this open interval AB to some real numbers, that function exists independently of any coordinate choice. Okay, that function exists independently of any coordinate choice. Now, what we can do is we will differentiate this function, okay, to give us the tangent, and we'll get the tangent at some special point, which we'll call t is equal to 0. Okay, so we will define df dt, okay, and we can, again, we're going to, so this df dt always exists, but the right hand side of this is expressing it in a particular coordinate system. Okay, so in a particular coordinate system, as long as this coordinate patch is valid at the point t is equal to 0, we can write it as partial f partial x mu times dx mu dt, okay, where this dx mu dt is evaluated along the curve c of t. Okay, so it's evaluated along this curve c of t, and we're evaluating it at the point where t is equal to 0. That is, we're evaluating it as the curve is passing through the point P. Okay. Okay, so the information about which curve you're using is here. It's in this dx mu dt. Okay, this partial f partial x mu is just the derivative of this function on the manifold evaluated at, okay, now you're evaluating it at some point on the curve. Okay, but the key point is this quantity. Okay, now this quantity, okay, another way of writing it is we can write this df dt, okay, as some operation that we're performing on the function f. Okay, and what is this operation? Well, the operation is where we can write our operation as x mu partial partial x mu. Okay, I hope this notation is clear. The notation we're using here also is there's a summation over mu is 1 through n, right, where I'm summing over all my coordinates. Again, it's similar to the special relativity convention of repeated indices being summed. Okay, so mu is equal to 1 to n. So this is the Einstein index summation convention. Okay, so I'm going to drop these summation signs, but whenever you see this repeated index, okay, that means that there's a sum over all the indices, mu is 1 through n. Why n? Because there are n coordinates, x mu goes where mu goes from 1 through n describes the coordinates of any point. Okay, so so now we can write this df dt. Okay, remember that this left hand side, this df dt exists independently of what coordinate system you choose to write it in. Okay, is some operator acting on the function f. Okay, what is this operator? This operator, we can write it as x mu times partial partial x mu. Okay, this is in a coordinate representation. Okay, and what is this capital X mu? This capital X mu is just this quantity. So I've just called this x mu. This is dx mu dt along the curve c of t. evaluated at t is equal to 0. Okay, so this is the operation that we're performing on the function f, and this operation, when we perform it on the function f, gives us df dt. Okay. 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 I hope this is clear. Any questions about this?
Sir, can we try to correlate this to the delta? I mean the del sort of 4 vector that we had in special relativity, sort of. I mean the partial fraction term. Can we? I suppose we can. I mean, I'm not very clear about how, but I think we should be able to do something like that. Is that correct?
Yeah. Okay. So I'll sort of make that connection soon. Well, it'll take a couple of classes to make the connection to special relativity, but this partial x mu in sort of what we consider a Minkowski space. So first of all, Minkowski space means you have a metric. At the moment, we don't have a metric. Okay. So this partial x mu just represents the collection of derivatives partial t, partial x, partial y, partial z. Okay. How did we denote this in special relativity? This collection of derivatives?
So this was the covariant. Operator.
Good. It was the covariant derivative. So it was something like this. This is the shorthand notation we used for it. Okay. Right. Now, one thing that I will sort of point out, but maybe later, is that in special relativity, at least in the course when I taught you, the partial mu lower, we defined all our 4 vectors in terms of contravariant 4 vectors, and covariant 4 vectors were simply related to the contravariant 4 vectors through the metric. Okay, so we defined these. Now we don't have a notion of a metric yet. Okay, so at the moment we're defining covariant 4 vectors sort of independently of the existence of these contravariant 4 vectors. Okay, so these things will sort of exist independently, and later when we talk about metrics, we'll see what the connection is between the covariant and the contravariant 4 vectors. Okay. Yeah, so I'll try to make that connection a little more clear later, but at the moment, if you have a 4-dimensional manifold, okay, this is all I mean by the symbol. Okay, and we'll continue to denote it like this, but at the moment we're not making a connection between this quantity and the quantity with these minus signs, because those are related by the metric. Okay, which we'll talk about later. At the moment, all I mean by this, okay, is just this collection of 4 derivatives. This partial x mu just means this collection of 4 derivatives. Okay, for each value of mu. Okay, any other questions? Yeah, part of the challenge is that the framework is a bit elaborate, okay, and in special relativity, we're sort of throwing in everything together at once. We're not making the separation between topological space, manifold, and metric space. And so when we carefully make these separations, and actually the separation is needed in general relativity, once you make those separations, then because in fact you're solving for the metric, okay, in general relativity, right? As we discussed earlier, you're trying to figure out what the metric is. So if you have a space without a metric, that is a manifold. Okay, and so there are some properties which are just associated with the manifold which have nothing to do with the metric. And so it's good to separate out what those properties are. And by being careful about this, okay, by being careful about what properties are properties of the topological space, what properties come from the space being a manifold, that is having these smooth charts, versus what properties come from having a metric. Okay, it's good to make this separation, and once we make that separation, and once we discuss what it means to put a metric on the space on a manifold, then it'll be easier to make the connection to special relativity. So you'll have to be a little bit patient, where till we develop the full framework. Otherwise, it's going to get a little confusing if we try to jump ahead without fully developing the notion of the metric space as well. Okay, so we'll do several examples at a later stage, which will and we'll also talk about how special relativity fits into all of this. Okay, in this language. Okay. Okay. So now here's the thing. Okay. So this X itself. Okay. So now what we want to do is we want to define X. Okay, which is this X mu partial X mu. So so this derivative df dt, okay, was equal to some x of f. Okay, and now what we want to do is we want to define a notion of a derivative at this point P. Okay, but this notion of the derivative, sorry, the tangent, okay, or this point P, or the tangent vector at this point P, should not depend on this function f. Okay, I don't want to specify a function on the manifold to define a vector, right? The vector should exist independently of this function. So the sort of clever way that mathematicians define this vector is to define this operation itself. The operation. So when you take df dt as the tangent, you write it as x of f. Okay, and x is an operation. Okay, it's an operation that you perform in functions. This operation itself is defined as the vector. Okay, so the operation itself is defined as a vector. Okay, and clearly this operation, because these coefficients x mu, they are dx mu dt, okay, evaluated at t is equal to 0. So one way you can think about this is in coordinates, okay, roughly speaking, you can think about this as how fast my coordinates are changing as I'm moving along t, right? So as I'm moving from A to B, okay, so this is I'm varying my t, okay. This roughly tells me how fast I'm moving along the curve, okay, which in coordinates tells me roughly how fast my coordinates are changing. Okay, so that's telling me this dx mu dt. So it's some way to think about it. One way, if you can think about it, it's like a velocity. Okay, it's some kind of velocity along the curve at some point. Okay, so so this x mu which is defined as this dx mu dt, clearly depends on the curve itself. Okay, it depends on this map. Okay, from AB to this curve. Okay, so so for different curves, you will get different answers. Okay, for this. But this entire operation, okay, this x, which is x mu partial x mu, this operation only depends on the curve, but it does not depend on the function f. Okay, so for any smooth function f, as long as you can differentiate that function f, you can apply this operation to it and get things like df by dt. Okay, so so this operation itself is used to define a vector, okay, or what is called a tangent vector. Okay, so this operation of df dt will equal to x mu partial f. Sorry, this x is a differential operator, and x itself is what we call a tangent vector. Okay, and it satisfies several nice properties of what you would want in a vector. Okay, and if for different curves, you'll get different operators. Okay, and we'll see that all those curves together, I mean, all those differential operators together make up a vector space. Okay. Okay, so let me now formally define what we mean by a tangent vector on M. Okay, so we define this operator x, okay, which is such that df dt is equal to x of f for any smooth f. Okay, this defines, okay, this operation x this operation x is like taking the tangent, okay, or computing the tangent, but it's computing the tangent along a particular curve. Okay, so this x of f is x is an operation along a curve. It's an operation associated with a curve. Okay, a curve and the point at which you're trying to evaluate it. So we're evaluating at the point at some point t is equal to 0. Okay, and this operation then is associated with this point t, which is the c of t equal to 0, which is the point p on the manifold. Okay, the special point that we chose. And so now we associated this x with the point p. Okay, so this defines one tangent vector at the point p. Okay, so a couple of important points to remember. One is that the operation x itself is independent of the function f. Okay, for any function you can define this operation, and the operation is the same. Okay, the operation that you perform is exactly the same. So it independent of f, you only get one vector. Okay, for one curve. So x depends only on the curve c. Okay, it only depends on this curve. And the other point is that this operation x is independent of the choice of coordinates. Okay, because as I told you, this df by dt is a derivative that exists independently of any choice of coordinates that you put on the manifold. However, you can represent this in a particular coordinate patch, and if your coordinates are x mu, then you can represent capital X as some capital X mu partial x mu, where this capital X mu is dx by dt at t is equal, evaluated along the curve at t is equal to 0. Okay. So these are the three important points about what this vector is. This x is independent of f, only depends on the curve, and it's actually independent of the choice of the existence of x is independent of the choice of coordinates. You can use a particular set of coordinates to express x. Okay, like this. Okay, so let's do a simple example. So let's take a particular function. Okay, so I'll call it, let's say, f mu. Okay, where mu can be 1, 2, or anything up till n. So I'm choosing one of these. Okay, and we're choosing this function on the manifold, at least within the coordinate patch. Okay, at least within the coordinate patch, we're choosing the function. Okay, sorry, yes, is there a question?
Yes, sir.
Okay.
I just want to ask. You said that x depends on the coordinate system also, right?
This capital X?
Okay, so you have written so it should depend on the coordinate system, I think, because in the denominator, so we have this del by del x mu term, right, in the definition of this operator x.
No, the operator x does not depend on the coordinate system. Okay, it only depends on the curve. Okay, you can express it in a particular coordinate system this way. Okay, but there's equivalent expressions that you can use in any other coordinate system. So in another coordinate system, I'll write it as some y mu coefficients partial y mu. We'll see how to make this transformation also between coordinate systems. But this operation x itself is a unique operation that doesn't care about which coordinate system you're using.
Okay, sir. Yeah.
Okay, just as what we discussed, this df by dt, right, is this operation of differentiating f along the curve is independent of any choice of coordinate system, because the curve itself, okay, the curve itself is a function. I mean, you can directly think about from AB to R, there is a function f circle C. That function can be differentiated. Okay, that operation doesn't rely on any coordinate system. Okay. Okay, so now what we'll do is we'll take functions f mu, okay, where mu is for different choices of mu, we'll just take a simple choice. Okay, so any point here will have coordinates x1 through xn. Okay, so I will choose the function f mu such that it returns the muth coordinate. Okay, so it returns the coordinate x mu. Okay, so in other words, f acting on a particular set of coordinates. Okay, strictly speaking, if I was mathematically precise, I'm going to the coordinates and then I'm going to the function f. So how should I think of this operation? If this is phi and this is f, what is the right way to think of this operation? What do I really mean? This is a very bad shorthand notation, which we will use often, but we should be clear what the exact meaning of this is. What do we really mean here? Okay, this is what I'm trying to represent. It's a map from coordinates to the function f. But what do I really mean when I'm doing this? Something like this.
F composition phi inverse.
Very good. Yeah. So first phi inverse, then f. Okay, that's what we really mean. But in shorthand, we'll just write it as f of x1 through xn. Okay, it's actually f compose phi inverse acting on x1 through xn. Phi inverse takes me back to the manifold. Okay, and the function actually acts on the manifold. It doesn't directly act on the coordinates. Okay, in shorthand, we will drop this. Okay, once we know which coordinate system we're talking about. Okay, so f mu is equal to x. So if we're choosing some function f mu, which is x mu, that is, it returns the muth coordinate. Okay, so this we're defining as I take a function which I label as f mu and it returns x mu. Okay, so that is f mu gives the muth coordinate. And now what we can do is for this particular function, this function is a map from the manifold to the real numbers. Okay, and at least this function, in this coordinate representation, is valid within this coordinate patch that we're using. Okay, so now let's compute what this operation x on f mu does. Okay, so x acting on f mu, as we've already written, is dx nu dt partial x nu, and f mu I've just written as x mu over here. Okay, and this entire thing is to be evaluated at t is equal to 0. Okay, and so when I evaluate it, what I get is, so here the new index is summed. Okay, the new index is summed, and that new index is part of the operator x. So x, remember, is dx nu dt partial x nu. Okay, where this is evaluated at t is equal to 0 along the curve c of t. Okay, and here I'm putting f mu, and f mu just returns x mu. So that's what I put over here. Okay, and what is partial x mu, partial x nu? What is that going to give me?
Del mu.
Yeah, that's just a delta, Kronecker delta. Okay, if mu is the same as nu, it's 1, otherwise it's 0. Okay, and so we'll write it like this. And this delta mu nu, when I take it with dx nu dt and I sum over nu, it only picks out the nu value, which is equal to the mu value. So I'll only get dx mu dt. Okay, I evaluated at t is equal to 0. So that is this x of f mu. All it does when it acts on these particular functions, okay, is it picks out the muth component of the velocity. If you think of t as time, it's like picking out the muth component of the velocity vector. Okay, so a simple way to think about this is, imagine that your manifold is really isomorphic to our let's say Rn or R cube. Okay, so this is like your x, y, z. And so this is your curve going through this space. Okay, and what we did was to say that our function f mu, let's say f1, returns the x coordinate, okay, of your trajectory. Okay, then x acting on f1, all it does is it returns for me dx dt. Okay, and if I think of t as some measure of time, let's say it's actually the rate at which I'm moving along, moving to different points on this curve. Okay, then dx by dt is in some sense a measure of the velocity along the curve. Okay, yeah, okay, it's a measure of velocity along the curve. Okay, but we don't define our tangent vectors as this dx by dt. Okay, because that would rely on the choice of these functions f. Okay, and these functions here we made a particular choice where we chose them to be coordinate functions. But we want a definition that doesn't rely on coordinates. So we define the operation x itself, okay, to be the vector rather than dx mu by dt to be the vector. Okay, and the operation x itself does not rely on any coordinate system. Okay, and that's the reason why we choose x, and that's the reason why it's a little strange, because normally you like to think of vectors as you typically don't think of them as operations. Okay, but operations can also form a vector space. Okay, the sense that vectors can add, you can scale the vectors by something, and so on. Okay, So this choice of f of x as the or these operations x along a curve. Okay, these operations are define a vector. Okay, at the point P. Okay, any questions at this point? Okay, so now I'll just make one slight change of definition, okay, going forward. So we'll extend our definition actually. So previously we had associated x with a single curve C of t, okay. Now instead of associating x with a single curve C of t, we'll associate x with a family of curves, okay. So we'll say that two curves, that is, if we have two curves C1 and C2t, okay, so imagine these are the two curves and they both pass through the point P, okay. Imagine that both these curves pass through the point P. So that is C1 at t is equal to 0 and C2, so this is C curve 2, this is curve 1, at the point t is equal to 0, okay, give you the same point P on the manifold, okay. And the second important property is if the this operator x, okay, for the curve C1t is the same as the operator for C2t, okay, at the point t is equal to 0, okay, that is at this point, if both these operations are the same, okay, then you say that then we'll say that these curves are related. Okay, we'll say that there's a relationship between these two curves at the point P. Okay, these curves are related at the point P. Okay, so what do we mean by the operators being the same? Well, we can think of it in a coordinate representation. So what we're saying is dx mu dt for curve 1, okay, times partial x mu, okay, this quantity, okay, which is x evaluated on curve 1, is equal to dx mu dt on curve 2, okay, partial x mu, again evaluated at t is equal to 0. Okay, if these two quantities are the same, okay, then we say C2 is the same as C1. Okay, in other words, what we want is dx mu dt at t is equal to 0 is along curve 1 is the same as dx mu dt along curve 2 at t is equal to 0. Okay, visually, again, if you go back to our three-dimensional example x, y, z, okay, just usual Euclidean space, and you imagine some curve through it, okay, then roughly what we're saying is that you have another curve passing through the same point P, where the velocity at the point P is the same on that curve. Okay, so it has the same tangent at this point, but it could be doing something else when it goes far away. Okay, so the velocity at the point P is the same. The velocity being defined as this dx mu dt. Okay, I say velocity, but really it should be velocity in quotes because t is just a parameter along the curve. It's not really a time coordinate. Okay, it's just some parameter that tells me where I am on the curve. Okay. Okay. Because later we'll see that the manifolds that we're considering are actually space-time. So we're really talking about, let's say, x, y, z, and t, and we have some parameter lambda which describes. So we're trying to describe a path through space-time. Okay, and this path through space-time is some parametrically given by x of lambda, y of lambda, t of lambda, and z of lambda. Okay. And so what we're saying then is that all of these functions, if I take dx d lambda, okay, and dy d lambda and dt d lambda and dz d lambda, those are the same for two different curves, okay, at some particular point. Okay, if that is true, if it is true that both these curves have the same velocity at this point, okay, again, velocity is in quotes, then we say that the two curves C1 and C2 are related at this point. Okay, at the point P, C1 and C2 are related. Okay, there's a relationship between them. And the relationship is such that C1 and C2 will both yield exactly the same differential operator X. Okay, so this is not surprising. Okay, and you can again argue that this relationship that we found between two curves is an equivalence relation. That is, it partitions all curves passing through the point P okay, into equivalence classes. So all of those curves which have the same velocity, okay, at the point P, all of those fall into one member of the equivalence class. Okay, so one set of curves gives you one x. Okay, another set of curves gives you another x. Okay, another set of curves gives you another x. Okay, and the x for this set is different from the x for this set and is different from the x for this set. Okay, so rather than associating x with any particular curve, you're associating it with a family of curves. Okay, that's the only difference from what we were saying before. So in words, what I'm saying is we associated x now with an equivalence class of curves, C of t, such that all these curves pass through the point P and they yield the same tangent operator x. Okay, so all of them give the same tangent operator x. Okay, so now each equivalence class, that is, if I get an equivalence class C of t, you can tell me what the tangent operator is, and this gives me one tangent operator at the point P. Okay, or tangent vector at the point P. Okay, so this gives me 1x. And now the set of all equivalence classes, okay, that is, I take all possible equivalence classes, that is, and each one will give me a different vector, okay, and it will be different from all the others. So I'll get an x prime, x double prime, and so on. And I'll get what eventually, when I take all of these together, this yields a vector space at P. Okay. Okay, so formally now we'll define the tangent space at P. So this the set of all tangent vectors associated with these equivalence classes of curves, this vector space is called the tangent space of M at the point P. So on a manifold M, we now have a notion of tangent space. Okay, that is, we have a vector space that lives at this point. Okay, so you can think of its existence of this vector space as independent sort of or an independent space that's not part of the manifold. So similar to what we had pictured before, where we had sort of a tangent space like this on a sphere. Okay, you can picture it somewhat similarly in the sense that this tangent space will be n-dimensional if the manifold is n-dimensional. Okay, so for an n-dimensional manifold, you'll have an n-dimensional tangent space. Okay, and this tangent space will be denoted by Tp at M. This is the tangent space at the point P on the manifold M. Okay, so every point on the manifold will have its own tangent space. So this point here has a tangent space TPM. Okay, if this is the point P. If I have another point P prime, then that will have its own tangent space, which will denote as TP prime M. Okay, so each point comes with its own tangent space. Okay, and a priori, there is no way to relate the tangent space at one point to the tangent space at another point. Okay, and trying to relate tangent spaces at different points is exactly how we will be able to give a notion of curvature to a space. Okay, that's something that we'll see later. Okay, so at the moment, the tangent space at one point and the tangent space at another point on the manifold are completely unrelated to each other. And they are defined as operators. Okay, they're defined as operators. Each vector in this tangent space is defined as an operator. Okay, some kind of differential operator. And again, these vectors, just the fact that you've defined an x, the vector and the vector space itself at the point P, these are independent of the choice of coordinates. You can represent them in a particular coordinate system, but their existence has nothing to do with the fact that you've put any special coordinates on the manifold. Okay, I'll pause here for questions again. Tasha?
Yes, sir. Sir, like when you defined C1 and C2, like why are you choosing the same parameter T and this condition? Like, isn't it possible to choose a C1 at T equal to 0 equal to C2 T prime equal to some point equal to P? Because this t is just
yeah, you're absolutely right. It could have parameterized this differently, as long as what I mean by the special point is that it gives me the point P. Basically, this should give me the point P.
Yes, and in general, this t prime will not be equal to 0 if t equal to 0.
In general, it won't be. Okay,
Yeah.
this is an arbitrary choice that we're making just to label the point P instead of creating confusion by trying to reparameterize the curve in some different way.
Oh, yeah, okay, sir.
I suppose it doesn't really matter because, I mean, if you are starting from an interval AB and some A prime, B prime, you can always like translate, shift, squeeze, and
Yeah, exactly. You can always include 0 and you can always change your parameter value so that t is equal to 0 corresponds to some specific point P. Okay. I mean, you certainly lost some generality, but rather than create more confusion by introducing a t prime, it's just to say that what I really mean is that this is the point P. Okay. The parameter on the curve is not so important.
Okay, sir.
Anything else? Okay.
Sir, I wanted to ask.
Yeah, go ahead.
So if it's forming a vector space, then there would be a way to combine the family of curves to get a third family of curves, right?
Combine the family of curves. Which family of curves are you talking about? In the equivalence class?
So any particular family of curves will define one vector, and so we should be able to combine two families to form a third family, which defines the third vector, right?
That's right. Yes. So okay, I can do it in a coordinate representation. Okay, and you can see that easily. So if I take one x to be x mu partial x mu. Okay, and this is kind of like the velocity, right, along a particular curve. And I take another tangent vector, which is like this. Then combining them, I can add them, and I can add them with arbitrary coefficients. Okay, this gives me a third vector, which is c1 x mu plus c2 y mu partial x mu. And this I can define as my z mu coefficients. Right. So basically this has given me a third operation, which is different from the other two.
Okay, sir, but if the addition operation is like representation dependent.
No. Okay. So here I did it in a particular representation, but again, the existence of this vector and their addition properties, I've shown it, through a coordinate representation, but you can show the additivity of these operations independent. So, okay. So what you really have to show is the linearity rule, right? So what you have to show is that if I have, so what does x do? xf is df dt, okay, along some curve. Yf is df dt along some other curve. Okay, and now what we want to say is that it's possible to get a third differential operation, okay, which is C1. So let me just take the simple operation of adding them. Okay, so it's possible to define the addition of these two operators. Which I can write as some x plus y f. And even though these were on different curves, this was on some curve ct, this was on some curve c prime t, there exists a curve sort of c double prime t, on which I can think of this zf as being the which would have given me the operation zf.
Okay, sir.
Okay, we've not found that curve. Okay,
And the scalar operation would work trivially by scaling t.
The scalar operation, you mean by multiplying this?
Yeah, like alpha x.
Yeah. So this is just. Yeah.
Okay.
So roughly the argument is that there exists some curve for which this will be true.
Okay, sir.
Right. So it is coordinate independent. Okay. The fact that this forms a vector space. Okay. So yeah. Sorry. By the way, I mean I'm assuming that all of you are familiar with the basic idea of a vector space. If not, I suggest you read. In chapter 2 of Nakahara. It's not a very long section, because we already did most of it when we covered topology. There's a brief discussion of vector spaces, and you can go through that for the properties of vector spaces. Okay, so things like the Leibniz rule, this additivity of the vectors and so on is defined. The one difference from vector spaces that you might be used to is that we think of these vector spaces as sort of, one way to think of them is column vectors. Okay, and which means that you have to have some kind of basis for this vector space. So let's do this next. Let's first define the basis, okay, and then I'll tell you what operation is not there in this vector space. Okay, basically the operation that's missing on this vector space is taking an inner product. Okay, there's no way to take an inner product, because taking an inner product would mean roughly you take a row vector and a column vector and you take the matrix product of those. Okay, there is no operation which can take you from a column vector to a row vector on this vector space. Okay, so this vector space is defined without an inner product. Okay, so that's the difference between this vector space and some of the vector spaces that you might have seen before. But if you've taken a course in linear algebra, this is probably familiar to you, right? I don't know, was this covered in your basic math courses? Vector spaces without an inner product?
Yes, sir. I mean, not explicitly, but we initially discussed everything assuming
Sorry, Anish, your voice is breaking up, so I can't hear you.
Sir, we initially discussed stuff assuming that there is no notion of inner product at all, and then like.
Yeah. So okay, so you can define vector spaces, and one property that you can add on is the notion of an inner product. At the moment, we've not added on that notion, so there is no inner product defined on this vector space. Okay, so this notion of x dot y, or some way to take an inner product of 2 4 vectors, this is not defined. Okay, but all the other properties that you think of a vector space, so in particular what that means is x is not defined, so you can't take the norm of this vector. You don't know what its magnitude is, okay, in some sense. Okay, but you can find a basis. Okay, you can find a basis, and any vector can be expressed in terms of this basis. Okay, so what you need is a linearly independent set of basis vectors. Okay, and that's what we'll do next. We'll try to find a basis for this vector space. Okay. So what we've seen is that any vector x can be expressed as some x mu, partial x mu, at least in some coordinate system at the point P. Okay, so we're assuming some coordinates are x mu are valid at the point P. So now what we can do is now the vector space is n-dimensional. Okay, and each of these partial x mu's are independent. So we can define our basis vectors as this operation, as the derivative along the x mu direction. Okay, we can define those as our basis vectors, and these basis vectors, so this is a definition of what we mean by the basis vector. And now these basis vectors can be used as a vector basis for TPM. Okay, now there's something very important here. TPM is a tangent space. The tangent space exists independently of any coordinates that you choose to assign to it. Okay, because these vectors x exist independently of any coordinates that you choose to assign. But this basis that we're choosing is a special basis because it relies on a particular coordinate system. Okay, so the basis that you choose can be coordinate dependent, and so this is called a coordinate basis. Okay, this is called a coordinate basis. Okay. So any general vector now that belongs to this tangent space, we can express it as some coefficient, okay, which you can think of as the components of this vector v times the basis vectors, okay, times e mu, where again there's a summation over mu. Okay, so when you write a column vector, what you really mean is this is what we think of as E1. Okay, E2 would be 0, 1, 0, 0, 0, and so on. Okay, so now it's just that our basis vectors themselves are defined using operations. Okay, they're defined using operations. Okay, and what we're really interested in is are the coefficients of these basis vectors. So really, we are interested in something like this. Okay, this is sorry, v1, v2, v3. Okay, yeah. So sorry. The basis you should just think of as, okay, it's some basis. Okay, this e mu's, and these coefficients tell us how much we're adding along different directions in this space of basis vectors. Okay. One important thing is, one really important thing is, again, since we don't have a notion of inner products, there's no sense in which we can say that two basis vectors are orthogonal to each other. Okay, and since we don't have a notion of inner products, we don't have a notion of magnitude of the vector. So there's no sense in which we can call this a unit vector either. Okay, so this is neither a unit vector. Okay, we can't think of it as a unit vector because there's no notion of magnitude. And we can't think of this as an orthonormal basis also, or orthogonal basis. Okay, no notion of orthogonality. Because again, for orthogonality, you need to define inner products between vectors. Okay, so only basically the additivity properties and the multiplication by real numbers and scaling, okay, those properties of the vector space are preserved. Orthogonality, anything that relies on the inner product, in particular orthogonality and defining unit vectors, those are ill-defined things, okay, because we don't have a notion of an inner product on this vector space. Okay, so yeah, okay. So any general vector in this vector space can be expressed as v mu, where v mu are the components of v in this coordinate basis. Okay, and the dimension of the tangent space is equal to the dimension of the manifold. Okay, where the manifold is defined as a topological space which is homeomorphic to Rn. Okay, and so the dimension of the manifold was n, and therefore the dimension of the tangent space is also going to be n. Okay. An n-dimensional tangent space for an n-dimensional manifold. Okay, now, one thing is that since the tangent vectors themselves, each of these x, are independent of your particular coordinate choice, it should be true that now you should be able to translate smoothly from one coordinate basis to another coordinate basis. That is, supposing I have a manifold M, okay, which I've shown here. This is my vector x. Okay, so there's only one vector x, but I have different coordinate patches. Okay, let's draw them like this. So, and in the left coordinate patch, this point P, okay, which lies in the intersection of these coordinate patches, in one coordinate patch, I give it the coordinates small x. Okay, in another coordinate patch, I give it the coordinates small y. Okay, and now I can express this x in either coordinate basis. Okay, so I can use this coordinate patch to define basis vectors partial x mu. Okay, I can use this coordinate patch to define basis vectors as partial y mu. And therefore, the same vector x can be expanded in a series of coefficients times partial x mu, or it can be expanded in a series of coefficients times partial y mu. Okay, and both of these expressions should perform the same operation. Okay, because it's the same vector that you're talking about. So the fact that both of these perform the same operation is going to give you a relationship between the coefficients in one basis and the coefficients in another basis. Okay, and that's easy to see. Okay, we just use the chain rule. Okay, so x mu partial x mu can be written as, so instead of writing the dependent variable as x mu, we can now change the dependent variable to y. Okay, and we just use the chain rule here. So we write it as partial y nu, partial y nu over here. Okay, and now we can imagine grouping these terms together, okay, into something like this. So x nu, sorry, I'm fiddling with the indices a little bit. So in this step, I'm changing my mu in this. So mu is summed over and nu is also summed over. So I'm changing mu to nu and nu to mu. Okay, so I'll x nu partial y mu partial x nu partial y mu. Okay, these are dummy indices because I'm summing over them. Okay, I'm summing over mu and summing over nu. Okay, and therefore I can change the label of what I'm calling mu and mu. And so now this entire coefficient is now precisely what I'm calling y mu. Okay, so this is y mu partial y small y mu. Okay, and so therefore I have an expression for the new basis coefficients, the new vector coefficients in the new basis, and I can relate them to what they were in the old basis. Okay, so y mu is just partial y mu partial x nu times x nu. Okay, so it's a very simple transformation rule to relate the vector coefficients in the new basis to the vector coefficients in the old basis. Okay, it's the same vector just expressed in a different basis. Okay, and the basis is different because it's a coordinate basis, and if you change coordinates from x to y, you will get a different basis. Partial x mu becomes this new basis of partial y mu. Okay, and you have to express all of these in terms of this new basis. Okay, so this gives us the rules for how the components of a vector change when you're transforming from one coordinate basis to another coordinate basis. Okay. Okay, and yeah, so the last thing about these vectors is that you can also choose a non-coordinate basis. Okay, the coordinate basis is not sacred. You can choose a basis which doesn't rely on your coordinates. So you can take any general linear combination of your coordinate basis vectors, and that general linear combination, okay, as long as you choose a rank n set of combinations. Okay, so formally what you define is you define a new basis e hat I, okay, where I runs from 1 through n. E hat I is equal to some coefficients ai mu. Okay, so the sum is over mu. Okay, it's not over I. Okay, so essentially what this is it's taking your E1, E2, En, taking some particular, multiplying by some matrix A, okay, and it's spitting out for me some linear combination of those, okay, and that new linear combination is what I'm calling E hat I, which is my new basis vector, okay, and this AI, this matrix A, okay, which in components is AI mu, this should belong to a general linear transformation, okay, from n variables with real coefficients. Okay, so it's an n by n matrix of real coefficients. I think the only thing is that it has this determinant of A should be non-zero. Okay, the determinant of A should be non-zero so that you get a complete basis. Okay, of n vectors. Okay, you want n linearly independent combinations of these. Okay, we'll pause here. Any questions? It's really important that you get this idea of vectors clearly and the idea of defining them using operations, okay, using this derivative operator, which is coordinate independent.
Sir, what is the exact difference between a coordinate basis and a non-coordinate basis? There
could be some coordinates for which this is the basis. Okay, this E hat I is the basis. All I'm saying is that I don't have to have. So for example, suppose I have a manifold, okay, and I have some basis. So I have some set of coordinates. Okay, suppose there's only one coordinate patch that covers this point. So there's one set of coordinates x mu. Okay, now the bases are therefore these quantities. Okay, in other words, it's partial x1, partial x2, and so on. Okay. Non-coordinate basis simply means that I'm taking linear combinations of these and calling those my basis vectors. And that's also a perfectly valid basis, even though there are no coordinates specifically associated with those linear combinations. So for example, okay. Yeah, I could take this combination. Okay, and I could use this to define a new basis vector. Okay, and I mean I have to define a complete orthogonal, not orthogonal. I have to define a complete linearly independent set. Okay, using these basis vectors. Okay, any other questions?
Sir,
Yeah.
sir, can we say that A inverse should exist, or else the inverse transformation will not be there? Like,
Yeah, that's why I said determinant of A is non-zero. You need to
yeah,
impose this condition.
yeah.
Yeah, so I'm not sure if general linear transformations. I'm not sure if this. So this is formally there's some group, okay, labeled by general linear matrices of, and I don't know if this includes the condition that the determinant of these matrices is non-zero. I suppose it does actually. Okay, but I have to check. But in any case, this condition needs to be imposed. Okay, if you want to get a new basis.
Sir, it does include that condition. Like I just checked.
It does include that condition, right? Yeah. Yeah, so this, let me just explain, because this will show up in other places. This is called general linear transformations or general linear n by n matrices with real entries. Okay, and where the determinant of these matrices is non-zero. Okay, the set of such matrices forms a group under the operation of matrix multiplication, and that group is denoted as GLNR. Okay, so any element of that group you can take and use that to define a non-coordinate basis. Okay, so let's move on. We'll start a little bit of this dual vector space, okay, and then we'll continue next time. So so just again to summarize, so basically the idea of a vector space, okay, TP at M, is associated with every point P on the manifold. You now have a linear vector space TPM, okay, and this dimension of this space, okay, is the vector space TPM. This is n. The dimension of the manifold, that is also n. Okay, the dimension of a vector space is very different, a very different notion than the dimension of a manifold, right? The dimension of the manifold has to do with the homeomorphism between the manifold and Rn. The dimension of the vector space has to do with how many linearly independent vectors there are that make up the vector space. Okay. Now, this space was defined using derivative operators defined on an equivalence class of curves which pass through the point P. Okay, and again, I'll emphasize again that each point P on the manifold has its own tangent space. Okay, has its own tangent space, and in general, there's no relationship between these different tangent spaces. Okay, on an arbitrary manifold. Okay, now we'll come to the notion of a dual vector space. Okay, so now the idea is that given any vector space V, okay, it doesn't have to be these vector space on the at particular points on the manifold. This is true for any general vector space V. It is always possible to find a dual vector space. Okay, and this dual vector space is denoted as a V star. So V is the vector space, which means V in our case was the entire tangent space at that point on the manifold. And now you can find this dual vector space such that if you take a vector which will denote as W star, which belongs to this dual vector space V star, and if you take a vector V which belongs to the original vector space V, capital V, then you can define an action, okay, of the dual vector on the original vector. Okay, so it's possible to define an action W star acting on V such that for every dual vector and every vector, this returns to you a real number. Okay, it returns to you something that belongs to real numbers. And this one way to think about this operation of W star acting on V is to define it as an inner product. Okay, so it's some operation. In quantum mechanics, you might have seen this notation where you write a ket and you write a bra. Okay, so we'll use similar notation here. So, so this is very similar to quantum mechanics, in which you define ket states as some psi. Okay, as these are some vectors in the Hilbert space. Okay, it's some vector in the Hilbert space, and you define bra states chi that live in a dual Hilbert space. Okay, so we don't usually think of the distinction between them, but really these bra states live in a different space. Okay, that's called a dual Hilbert space. And you can take an inner product between a bra state and a ket state. Okay, in quantum mechanics, this result of this inner product is a complex number. It's not a real number. Okay, but you can do something similar on any vector space, and in particular, you can do this on what are called real vector spaces rather than complex vector spaces. And you can define the inner product to be a real number. Okay, so you can define the inner product of some dual vector with an original vector to give me a real number. Okay, so that's what we're going to exploit, and we're going to use this to define a dual vector space to TPM. Okay, which means you take the tangent vector space at the point P. Then associated with this point P, we define a dual vector space, which will denote as TP star M. Okay. Again, this new vector space, this dual vector space, also is associated with a specific point. It's associated with this point M. And these two vector spaces are dual to each other. Okay. So the vectors omega here and the vectors V here, it's possible to take an inner product of these, okay, of these vectors. Okay, and the inner product will be a real number. Okay, that's the other point. Okay, so we will define the dual vector space as TP star M. Okay, so it's the dual vector space. It's also called the cotangent space. Just like TPM is called the tangent space, this is called the cotangent space. Okay, and you take a vector W which belongs to the dual vector space, and a vector V which belongs to the original vector space TPM, and it's possible to define the action of the dual vector on the original vector, okay, as some kind of inner product which returns a real number. Okay, and so now what we can do is we can define a specific dual vector W, okay, on TP star M. Okay, so we'll define a specific vector. And we'll define it in terms of a function f. Okay, so we want to choose a W, okay, some vector from this dual vector space, and we want to give it a label, and we label it based on a function f, which is some smooth function on M, or at least at the point P. Okay, so at least at the point P on this manifold, there's some function from this manifold to real numbers, and this f is a smooth function, okay, from this manifold to real numbers. And associated with this f, I will now define an element of TP star of M. Okay, associated with this function f, we will now define a vector in the dual vector space. Okay, so as long as this function belongs to smooth functions on the manifold. Okay, and this vector in the dual vector space, we will write it as df. Okay, now one important thing is let's not think of this as a differential operation in the sense that we usually think about, where we think of this as an infinitesimal difference. Right now it's just a symbol. Okay, the symbol is telling us that associated with this function f, we are defining a vector omega, which we are denoting as df, okay, on this dual vector space. So it doesn't have a notion of being a differential. It's just defined to be some kind of vector in the dual vector space. Okay. Okay. So at the moment, df is just a symbol. Okay. You shouldn't think of this as the differential of f. It's just df. It's some dual vector associated with f. Okay. Later we'll see that indeed it does have, in some sense, once you put a metric on the space, then it does get associated with the differential of f. Okay. But at the moment, there is no such meaning to associate with this. Okay. Now, if you have a vector belonging to the tangent space, okay, so remember at every point on the manifold, I have a tangent space, and we also have a dual cotangent space. Okay, so we have a vector v, and this vector v, which lives on the tangent space, is in some components, in some coordinate basis, is v mu partial x mu. Okay. And now we want to define the action of this particular vector df on that vector v. Okay, so we want to define the action of df on the vector v. Okay, and essentially that's some kind of inner product. We can write it as an inner product. Okay, we will define the action of this vector df on v as it returns basically v acting on f. Okay, and this is a number when I evaluate it at the point p. Okay, remember what this was? This is like df dt along, you know, some curve, right? The curve which has v as its tangent vector. Okay, so that's what we define the inner product to be. We define the inner product to be such that you pick the dual vector from this vector space such that the inner product of this vector, this dual vector with the original vector v yields, okay, this quantity, okay, at the point p. So in component notation, this is going to be v mu partial f partial x mu. Okay, and this belongs to real numbers. So it does give you a proper inner product. It returns a real number for you. So what did we do? We took a vector from here. We took a dual vector from the dual vector space, and we gave a prescription for what happens when this dual vector and this vector are dotted together. Then you get this quantity. Okay, and this is actually how you're defining these dual vectors. The df notation is defining the dual vector as you are picking the dual vector from the dual vector space such that when I take its dot product with v, it returns for me this particular number. Okay, this is why we are denoting the dual vector as depending on f. Okay, it depends on what f we're using. Okay, so this is picking out a particular dual vector for you which depends on f. Okay, and this is the result of the inner product. Okay, with v. Okay, so now that we have this, okay, now that we have this, suppose we take, again, we'll take our coordinate functions. Okay, so let's take f is equal to x nu. Okay, so we'll take our f is equal to x nu. That is the coordinate functions, and we'll take our vector v to be partial x mu. That is, we'll take only one of these v mu's to be non-zero. Okay, is 0, 0, 0, except for some particular v mu. Okay, so you're picking out one particular, sorry, and in fact it's just one. Okay, so you picked out some particular vector, okay, which in this is just along one particular basis vector. So that is, you picked a particular coordinate basis vector. And now what we want to do is we want to find, okay, so f is x nu. So that means df we can write as dx nu. Okay, again, remember that this is just a symbol. It doesn't mean the differential of x nu. Okay, it's just a symbol. It's telling me which dual vector to pick. Okay, and the rule is if I take now this inner product of dx nu with partial x mu. Okay, so this is a vector belonging to TPM. This is a vector belonging to the dual vector space TP star M. Okay, and this dot product between these two vectors is given by so again I should take partial f partial x nu. Okay, and f is x, sorry, partial f partial x mu. Okay, times v mu, and v mu is 1 only for this particular value of mu. Okay, so I'll just get this, and f is just x nu. Okay, so what I'm going to get is just partial x nu partial x mu, which we already decided is delta nu. Okay, so what you can do is now you can think of dx nu as a dual basis vector, such that when and you can think of this as a dual coordinate basis vector, in the sense that if I take my original coordinate basis vector and I take the dot product with this dual vector, then the result is just a delta mu nu. Okay, so that means that associated with every partial x mu state, partial x mu vector, so this belongs to TPM, you can find a dx mu which belongs to TP star M, such that the inner product of these two is 1. Okay, so that's what we mean by a dual basis. Okay, and the inner product, if mu is equal to nu, then it's 1. Okay, then the dot product is 1. If mu is not equal to nu, then the dot product is 0. Okay, then you get 0. If mu is equal to nu, the dot product is 1. Okay, so these dx nu form a dual basis for the cotangent space. Okay, for nu is 1 through n. Okay, so the dimensions, so since for every vector you have every basis vector, you have a dual basis vector, the dimension of the cotangent space is the same as the dimension of the tangent space. These are vector spaces, which is the same as the dimension of the manifold, which is n. Okay, where the manifold is isomorphic to Rn. Sorry, not isomorphic, locally homeomorphic to Rn. Okay. Okay, I think this is a good point to stop, so we'll stop here. Okay, any questions?
Sir,
Yeah.
sir, while defining vectors, we said that vectors are like independent of f, like they act on f, but we can define the vectors without f. But while defining dual vectors, why are we explicitly like using f?
Okay, that's a good question. So actually the dual vectors exist independently of the functions f. Okay, but I'm trying to pick a particular dual vector. Okay, this particular dual vector I can associate with every f. I can associate a particular dual vector. Okay, but that doesn't mean the dual vectors exist independently of the existence of a function defined on the manifold. Okay, but we're using functions on the manifold to pick out particular dual vectors. Just like the vectors x exist independently of any coordinates. Okay, but if you make a choice of coordinates, then I can pick out a particular x mu, for example. I can pick out particular vectors. Okay, so it's not that, so x star, or which belongs to the dual vector space, these exist independent of any functions. Okay, we're picking out a particular function, a particular dual vector, which we're denoting as df. And that the way we're picking it is by choosing a function and then finding a dual vector which corresponds to that.
So for any dual vector, there would be a family of functions associated with it.
Yeah, I mean, I didn't get into those details, but yes.
I presume it is like functions differing by a constant.
Functions differing by a constant. I mean, it's true over here. I mean, you can see it in the definition.
Locally differing by a constant.
Locally, you can yeah, you can change them by a constant. Yeah, so it's not just one function that gives you this dual vector. There are multiple functions that can give you the same dual vector, which all of these functions differ by a constant locally. Toshif, is that clear?
Yes, sir. So like so d of f and d of g are two different basis vectors in the cotangent space.
They could be the same.
Like provided they are not of like equivalent. Like if I assume that f and g are not of the same class.
No, it's not guaranteed. Okay, because yeah, okay, I think it is guaranteed. Yeah, if they don't differ by a constant, then you will get a different dual vector. I think that is right. So dg is not the same as df in general. I think that's true. It's a different vector in the dual vector space. If partial f partial x mu not equal to partial g partial x mu for all mu, then dg not equal to df. Right? Because basically I've only checked the action on one vector, but you should check the action on every possible basis vector. So take every possible v mu, right? And if partial x mu is the same as partial g partial x mu, then you will get exactly the same dual vector. Otherwise, you'll get a different dual vector. This is what Varad was saying also, that this means that they only differ by a constant in the coordinate, in terms of coordinates. Actually, that's also not true. I mean, this is only evaluated at a specific point. So, I mean, this is the exact condition. Okay, so I wouldn't say they differ by a constant because it's you're evaluating at a specific point. X of p.
So, sir, we can say that the dual vectors exist on their own, like, but to define this inner product, we are using a particular dual vector of that code.
No, it's the other way around. To define a particular dual vector, we're specifying what the inner product is.
Okay.
The inner product depends on f. Okay, this is a choice that we're making, and that specifies a dual vector which depends on f.
Okay, so now it's okay. Yeah.
Okay, so let's stop here and we'll meet on Thursday next. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.